Hello everyone. In this lecture on power electronics, we will be learning about applications of different power electronic circuits. So the first application that we will start is motor drive. Now motors can be AC motor or DC motor. The AC motor drive can be or AC motor speed control can be done in two ways. We can control the voltage input or we can control the frequency, that is the variable voltage drive or variable frequency drive. We can operate or we can use the variable voltage drive using single phase voltage controller that we have learned in SAC controller, or three phase voltage controller depending upon how our machine is. If the motor that is being considered is a three-phase motor, then we will have to use three-phase voltage controller. If it's a single-phase motor, we can use the single-phase voltage controller. And again, if we want to consider controlling the frequency of the input voltage and current, then we can use the cycloconverter, single-phase cycloconverter or three-phase cycloconverter. It is to be remembered that if we for the variable frequency drive, we are actually considering single phase motors, single phase AC motors, because in both the cycloconverters the outputs are single phase outputs. AC motor drive, we have already learned in case of controllers, that this is an example of voltage controller. This is an example of voltage controller. What happens is, this is our angle alpha, and if we increase this angle alpha, the output voltage decreases, because output voltage, instead of being the whole half circle, it can be this much or even shorter. So we can change the value of alpha to decrease the output voltage, and by increasing or decreasing the output voltage, we can increase or decrease the speed of AC motor. So this is how voltage controller motor drive works. In case of frequency controller, we can see that if the original frequency can be greatly decreased using ACSA cycloconverters. So using cycloconverters, we can also decrease the frequency, and with the decrease in frequency, the speed of motor decreases. That is, we can control the motor and the speed of it using using voltage controllers and cycloconverters. Exactly how these things are well learned in our lectures on ACAC controllers. Now for DC motor drive, the the method that we use is called H-bridge drive. Now any motor drive consists of two parts. Firstly, the direction, and secondly the speed. Now for DC motor drive, we consider both direction and speed using this circuit. If you look at this circuit very closely, the circuit will look like an inverter. It will look like a full bridge inverter, full bridge single phase inverter. And inverter is actually needed. Why is it needed? See, suppose this is our motor. So if we connect plus here and minus here, the motor will rotate in one direction. And if we connect minus here and plus here, the motor will rotate in opposite direction. That is, whether the motor rotates in clockwise or counterclockwise direction depends on the direction of the current flow through the motor. If current flow is flows in one direction, it moves in clockwise, and if the current flows in opposite direction, it moves counterclockwise. That difference in direction is created by using an inverter, which is called H-bridge. What it does is, see, this end here is motor. It is connected to the middle point between two MOSFETs. Now when we switch on MOSFET Q1 and Q4, what happens? Current flows in this direction. As a result, the motor rotates in one direction. And again, if we switch these two off and we switch on Q3 and Q2, the current flows in this direction, and as a result, the motor rotates in opposite direction. That is, the voltage across the motor is in one case plus here, minus here, and in the next case minus here and plus here, since the polarity of the voltage changes, and as a result the direction of the motor changes. That is, if we want to rotate the motor in clockwise direction, suppose we will switch these two on, If we want to rotate the motor in counterclockwise direction, we'll switch these two on and these two off. Now, this is an interesting phenomena. This is how the direction of the H bridges or the direction of DC motor is controlled. How is the speed of DC motor controlled? This is the speed of DC motor controlled is by manipulating the power through the motor. How can we do that? Instead of switching these and these on in clockwise rotation, if we provide pulse to the gates, we keep these MOSFETs on for a certain time and we keep these MOSFETs off for a certain time. Let us suppose that for the 50% of the time we keep them on and for the rest 50% we keep them off. If we do that, what happens is the total power virtually becomes total power supplied to the motor becomes half. As a result, the speed of the motor also becomes half. Instead of 50%, we can make 75%, 25%. We can change the duty cycle as we like, and by changing the duty cycle of the input of these gates, we can actually change the power consumed by the motor, which will in turn change the speed of the motor. If the power consumed by the motor rises, the speed rises. If the power consumed falls, the speed also falls. That is, using this H bridge, which has the same operating principle as an inverter, full bridge inverter, we can control the direction and speed of a DC motor. Before we further move into our discussion, there is an important rule which is called the right hand rule. The right hand rule says that if a coil of wire is wound around the conductor and the wire is current carrying, then if we hold the conductor in such a way that our fingers point to the direction of the current, then our thumb will point to the direction of north. That is, we know that if around the conductor a coil is made and current is passed through that coil, then a magnetic field is created, and of that magnet, if all the four fingers point to the direction of the current, the thumb will point to the direction of the north. So in this orientation, we'll have a north here and south here. But if the direction of the current was opposite, that is in this direction, suppose, then again the direction of the polarity of the magnet will change, and we'll have a north here and we'll have south here in that case. This right hand rule will be useful when we go on to have our discussion on stepper motors. Now, stepper motor is a motor where we can precisely control the angle by which the motor will be rotated. So in stepper motor, we can control its speed very efficiently, and we can control its angle very efficiently. This is a 4-pole stepper motor given in an example. So how it works is, at first the phase, we do not connect any voltage to phase B. We have connected voltage in phase A. As a result, the current flows through phase A in such a way that a south pole is created here using the right hand rule, and winding over here is just in opposite direction to the winding over here. As a result, if the current direction is in this way here, the current direction is the opposite way in the other side of phase A. As a result, if south pole is created here, a north pole will be created there. And the rotor itself has 2 poles, the north and south. The north will get attracted to the south and the south will get attracted to the north. As a result, the rotor gets locked in this position. Now, we want to move it by 90 degree. In order to move it by 90 degree towards the right, what we do is we turn off the power of phase A and we turn on the power of phase B, turn on the voltage through phase B. Suppose in phase A, the plus was connected here, minus was connected here. In this case, what we'll do is we'll turn off phase A and connect the plus to phase B, minus to this end of phase B. As a result, the south will be created here and north will be created here. Now, the rotor, which look like this, the upper side, will get attracted to this south, because here there is no polarity since no current passes through phase A. So north will get attracted in this direction and it will rotate by 90 degrees. Again, what we do, we want to rotate it further by 90 degrees. So what we do, we turn off phase B and we turn on phase A. We put the plus of voltage here and minus of the voltage source here, then what happens, this north over here gets attracted to the south pole created here, and the south pole which was here get attracted to the north, so it rotates by another 90 degrees. Again, in the next step, what we do, we put plus here, plus of the voltage source here, minus of the voltage source there. Then what happens is the south pole is created here, north pole is created here, so the motor again rotates clockwise by 90 degrees, and this step 1, step 2, step 3, step 4 are rotated, and the motor starts moving clockwise. So by controlling which phase get energized and what's the polarity of the state, we can exactly control the orientation of the motor or the angle of the motor. That is, we can rotate the motor by 180 degree, 90 degree, or 270 degree. Again, another thing is there, it has only 4 poles, but if we increase the poles of the motor, if we make it 8 poles or even more, if we increase the number of poles, we can have a precise control over the angle by which move. Here we are moving it by 90 degrees, we can move it by 10 degrees, 5 degrees, or even less. So by stepper motor, we can very precisely control by speed by controlling the phase current or phase voltages, and we can very precisely control the angle at which the motor will rotate. Now, if we actually wanted to rotate the motor in a counterclockwise direction, what would we do? If we want to rotate in the counterclockwise direction, we will just just alternate the polarity. That is, at first we had this. In the next step, what we will do is we will put plus here and minus here. As a result, the motor will get attracted or rotated in this direction. In the next stage, we will put plus here, minus here. The motor will rotate in this direction. In the next stage, we will put plus here and minus here. Motor will rotate in this direction. As a result, we can rotate the motor both in clockwise direction and counterclockwise direction, and we can precisely control the angle of rotation of the rotor in any of the direction as stated. Now, the circuit that is used to drive stepper motor is again H-bridge, or the circuit that we have seen in full bridge inverter. But here there are 2 full bridge inverter or 2 H-bridge, this one and this one. Each of the H-bridge is used to energize one phase. Suppose this is phase A. For simplicity of the diagram, the coil is drawn here, but we have to know there is a coil here and there is a coil here for phase A. For phase B, there is a coil here and there is a coil here. So what happens is, there are 2 ways to drive a stepper motor: full step and half step. In case of full step, what we do is we at first turn Q1 and Q4, this and this on, and all the other things are off. As a result, phase A gets energized with plus here and minus here, and phase B is off. As a result, here is a south pole created, and this north is getting attracted to that south pole. So this is the first step. In the second step, what do we do? In the second step, we actually do quite the opposite. That is, in the second step, we turn off Q1 and Q4 and we turn on Q5 and Q8. If we turn on Q5 and Q8, what happens is we have a plus of phase B here, minus of phase B here. So as a result, north gets shifted in the counterclockwise direction. And then again, in the next stage, we turn on Q2, Q3. In the next stage, what we do is we are turning on Q2, Q3, and we are turning everything else on. So we have these and these on. So that means in the phase where the positive is in now this direction and the negative is this direction. As we have stated, phase A has 2 coils, one is here and another is there. So what happens is the polarity is changed. Now the south pole will be created here and north pole will be created here. The north, in step 2, the north of the magnet was here, which will get rotated here. So as a result, in step 2 we will get north here, in step 3 we will get north here and south here. And in the next step, what happens is, in the step 4, what we'll do is we turn off the Q2, Q3 and we turn on only Q6, Q7. If we turn these 2 on, we'll get a plus of phase B here, minus of phase B here. If that is created here, the pole of B that was here will be south and this will be north. If that is the case, then what will happen is the knot which was there here in step 3 will rotate by 90 degree and move to this position, and this thing will again rotate. That is, in this way we can make this motor rotate in counterclockwise direction. If we want to make the motor rotate in clockwise direction, what we will do, we would at first follow the switching pattern of stage 4, then stage 3, then stage 2, then stage 1. If we move in opposite direction, we will be moving in clockwise direction. This is how a stepper motor can be driven with a constant speed. The speed will depend on how frequently we switch from one step to another, and the angle at each step will be 90 degrees, because at first we had knot here of the magnet. The magnet was like this, then magnet became like this with knot here, then magnet became like this with knot here, and then magnet became like this with knot here. So at each step we'll move through 90 degree, and this is called the full step method of driving a stepper motor. The next method of driving a stepper motor is called half step method. Here the step angle, that is angle at which it will rotate, is 45 degrees. Now how does that work? The logic is simple. At first the step 1 is same as that of full step, that is we switch on Q1 and Q4 and switch everything off. As a result, this south polarity is created and this north polarity is created because phase A is energized, and the motor looks like this. In the next step, what we do is we keep Q1 and Q4 on. That is, here we have south, here we have north, no problem with that. Again, we switch on Q5 and Q8. This is our Q5 and this is our Q8. Then what happens? We create a south over here, we create a north over here. So we have a south here, we have a south here and here, we have a north here and here. So this south is attracted towards this north and this north simultaneously. This north is attracted towards this south and this south simultaneously. So it assumes a direction like this. It will assume a direction similar to this. Here we'll have north, here we'll have south, and as a result it will be rotated by 45 degrees. In the next step, what we do, we turn off phase A and we keep the phase B on. That is, we have south here, north here, and no more polarities. That is, north will again move to 145 degree and this will again move to 45 degree. And in the step 3, we'll get a magnet that is in horizontal position. Similarly, in the next step also we'll keep the phase B energized as it was, and we'll energize phase A in such a way that we'll get south here, we'll get north here. That is, we'll be switching on Q2 and Q3, these two MOSFETs. If that is done, it will move to another 45 degree, and as a result, in 8 steps, it will move to 845 degrees, and moving through 845 degrees, it will complete one entire circle. So if we want to move in counterclockwise direction, we follow this switching pattern. If we want to move in a clockwise direction, we follow this switching pattern. So advantage of half step is we can control the angle with a precision of 45 degrees. That is, we can make the angle go 45 degree, 90 degree, 135 degree, like that. In case of full step, we could control only through 90 degrees. That is, we could make the angle 90 degree or 180 degree. So the same circuitry can be used for half step and full step, but in half step we have more precise angular control than in case of full step drive. This is how a stepper motor is operated in real circuits. That's all for this lecture. In the next lecture, we'll be seeing a practical life example of how battery is charged. If you have any queries regarding this lecture, please feel free to let me know in the discussion box.